So we left off here. Solving systems using matrices. There are a few different ways that you can use matrices to solve systems. One that includes using the inverse. We're going to focus primarily on the method or methods using augmented matrices. So here's what an augmented matrix looks like. You have your n by n matrix. With n rows and n columns. And in addition, you have this extra column, which is why we call it an augmented matrix, attached to the coefficient matrix. So this is technically an n by n plus 1, since we're adding in that extra column. And the notation, assuming that B is the column matrix that we are attaching, is simply A slash B. Okay, so if you see this notation in terms of matrices, this is exactly what we're talking about. We're just talking about one matrix, and we're just attaching that extra column matrix. Okay? So this is all stuff and background that we need before we go through the procedures. So this is what we're going to start with, and then what we're going to do is use elementary row operations. Which consist of a few things. You are allowed to multiply any row by a non-zero constant. You can swap or interchange rows. And the last thing you can do is add non-zero constant multiple of one row to another. So these are the three things that you can do. We're going to focus on a couple different methods. One will be Gaussian elimination, and the other is going to be Gauss-Jordan. So we'll talk about what the differences are between those two, but essentially they are one and the same. It's just for one of these methods you don't go all out, so to speak. Okay, so Gaussian elimination is essentially using, so you're going to use the elementary row operations until you get to an augmented matrix in row echelon form. And what that means is that 1 the first non-zero entry in each row is 1. Two, in consecutive non-zero rows, the first 1 appears to the right of the first 1 in the row above. Three, zero rows, meaning rows that have only zeros, are at the bottom of the matrix. And that is Gaussian elimination. Now, if we add a fourth condition, that a column containing a 1 has zeros everywhere else, then now we've introduced Gauss-Jordan elimination. So Gauss-Jordan is steps 1 through 4, and Gaussian elimination is simply 1 through 3. Okay, so this does kind of explain what your calculator is doing, not necessarily how to do it, but if you were to put a 2 by 3, 3 by 4, and so on, that kind of matrix in your calculator, and you tell it to put it in reduced echelon form, or in row echelon form, sorry, you're going to see that these three conditions are met. If you tell it to put it in reduced row echelon form, okay, that's what Gauss-Jordan essentially does for you. Okay, so for example, a matrix that looks like this is in which format? Or, well, it's in row echelon form, and we used, well, we didn't, but we're going to pretend that we did. It's in row echelon form, and we used Gaussian elimination to get this. Now, a matrix that looks like this is in reduced row echelon form, and we use Gauss-Jordan to get it to look like that. Okay, and we will be doing these things. What we'll do is review quickly one example. Maybe we'll just do one example with both methods and then call it a day as far as reviewing how to solve systems, and then we can try to get to eigenvectors and eigenvalues, which is the big theme for the unit. Okay, so let's say we have the system 2x plus 6y plus z equals 7, x plus 2y minus z equals -1, 5x plus 7y minus 4z equals 9. And we'll solve both ways using Gaussian elimination and using Gauss-Jordan. Okay, so if you kind of know where things need to go, meaning we want a 1 in the front left, top left entry, and then a 1 in the just to the below and to the right of that, and then a 1 to the right and below that, then the ideal situation here, well, first let's write the matrix out. This is going to be 2, 6, 1, 1, 2, -1, 5, 7, -4, and then we're just augmenting that with 7, -1, and 9. Okay, so this is the matrix representation of the system. And the first thing I would do, since I know I want a 1 in that top left position, is to swap rows, so I don't have to do that later. So I'm going to put 1, 2, -1, -1 on top, and I'll just rewrite everything else below. And now, again, keeping in mind where we're going, since I need a 0 here in the second row, first column, and in the third row, first column, my next step is going to try to be to eliminate the coefficients in these positions, and you can do that in pretty much one step. We're going to, let's see, let's say we double row 1 and subtract row 2. And that's going to take care of this row. Because if I double the first row and then subtract row 2, this becomes a 0. Okay, so that's the objective here. And if I multiply 5 times row 1 and subtract row 3, that'll give me a new row to work with down here. Okay, so if I do those operations, double the first row and subtract the second row, we get 0. 2 times 2 is 4, and then we subtract 6. That's negative 2. 2 times negative 1 is negative 2. Subtract 1. We get negative 3. Double negative 1, that's negative 2. Subtract 7, that's negative 9. Okay. And now we'll repeat the process to get that bottom left 0 as well. 5 times row 1, subtract row 3, we get 0. 10 minus 7 is 3. Negative 5 minus negative 4 becomes negative 1. Again, negative 5, and then we subtract 9, we get negative 14. Okay, are there any questions on how we went from this matrix to this one? Okay, what else do I need to get? This 3 we need to make a 0. Oh, yes?
How do we know which equation from top
Say that louder, sorry.
How do we know which equations are best to use?
Here?
Yeah, from there, how do we know that which one to
Should it go here?
Yeah.
Okay, because if we know Gauss-Jordan has a diagonal of 1s and then 0s in front of that, I know that I always want a 1 up here. So if I have any row that's got a 1 in it already, I'm just going to put that as the top row. Does that make sense? And then the easiest thing to do once you take care of this is to try to get zeros in these 3 positions. You can do these 2 zeros next simultaneously like we did here, just trying to cancel out the 2 and the 5 with this first row. And then now what we're going to do is get this last 0 in this position. Does that make sense? And really you can do it, well, I guess the only option, sorry, I shouldn't say you can do it with both rows. If you use row 1 again, then this doesn't stay 0, right? So you're going to have to use row 2 and row 3 so that when we linearly combine these first entries, they don't change. But then here, if I take, let's see, if I triple row 2 and then I add double row 3, that gives me a negative 6 and then a positive 6, so then I'll get a 0. So top row's good. 0, negative 2, negative 3, negative 9. And then now, if I triple row 2 and add double row 3 to everything here, so this is the one I'm changing, this is still going to be 0. This turns into 0 because negative 6 plus 6 is 0. And then we have negative 9 plus negative 2, so that's negative 11. And then negative 27 and then negative 28 added together is negative 55. Does that make sense? Okay, so now we have all the zeros taken care of. We got this 1 taken care of. All I need is for this to be a 1 and for this to be a 1. So what I could do is multiply row 2 by negative 1/2 and multiply row 3 by negative 1/11. So now I get 1, 2, negative 1, negative 1, 0, 1, and this becomes 3 halves, and then 9 halves, and then 0, 0, 1, 5. So now we have this in row echelon form. Okay. The idea is that once you get here, and this is a good skill for the eigenvectors and values, by the way. We're not just doing it because it's fun. You can use back substitution, work your way back to find out what z, x, and y are. Because this row represents what equation? Z equals 5. Right. And if z equals 5, then I also know that in the second equation, that translates to y plus 3 halves times z, which we know is 5, and that equals 9 halves. So then we get y is equal to negative 2, negative 3. 9 minus, negative 3. And then now that I know that z is 5 and y is negative 3, we go all the way back to the first row, and I get x plus 2 times y, which is negative 3, minus 1 times z, which was 5, equals negative 1. So that's negative 6, that becomes 5, add another, that becomes 10. So at this point we use back substitution, which means work your way back up to the top, knowing z, then you can find y, then you can find x. And then we have our solution. So we know z is 5, y is negative 3, and x is 10. Okay? And again, this is in row echelon form. If you type this in the calculator and tell it to do it for you, this is what it would spit out. Okay? So that's part A. Okay? Part B, use Gauss-Jordan. Okay? What I'm going to do is pick up at what point I would kind of change my method. So I'm going to go back to the matrix that was 1, 2, negative 1, negative 1, 0, negative 2, negative 3, negative 9, 0, 0, 1, and then 5. Okay? So from this step, on the left side we want a diagonal of 1s essentially and zeros everywhere else. Okay? We have a 0 everywhere else in the bottom row. So that's good to go. The next thing I would do is concentrate on getting a 0 in the other row above it in the position that it needs to be a 0. So what I'm going to do is focus on this position, try to eliminate that negative 3 somehow so that it turns into 0. So we can use row 2 and row 3 because then the only things that are going to change are the third and fourth entries. Does that make sense? Okay, so I'll do row 2 plus not row 3. How many times row 3? I mean 3 row 3. And then 1, 2, negative 1, negative 1. Oops, that's a line, sorry. 0. Negative 2 plus nothing is still negative 2, but now negative 3 plus 3 is 0. Negative 9 plus 15 is 6. And we have 0, 0, 1, and 5 still. Okay, so we have a 0, 0, 1. We almost have this row exactly the way we need it. What do I need to do to this row? Divide by negative 2. We like to say multiply by negative a half, but same difference, same idea. So we got 0, 0, 1, 5, 0, 1, 0, negative 3, 1, 2, negative 1, 1. So the bottom two rows are taken care of, and the idea is that you don't really do much with the first row until you take care of these bottom two, because what you'll do is cancel out the middle number using one row, cancel out the third number using another row. Okay? So that now, let's see, if I just simply do row 1 plus row 3, I get 1, 2, 0. And then 0, 1, 0, negative 3, 0, 0, 1, 5. Right? Oh, messed something up. What did I do? B column, which 1, 2, 0, this shouldn't be a 1, it should be 6. Okay? And then what's the last thing I need to do? So, row 1, subtract 2R2. So now we get 1, 2 minus 2 is 0, 6 minus yeah, something doesn't seem right. Where did I lose it? Ah, thank you. So this should be negative 1 here. So then when I add negative 1 with 5, this shouldn't be a 6. That should be a 4. Okay. Now things are looking better. 4 minus negative 6 is 10. There we go. And then 0, 1, 0, negative 3 is good. 0, 0, 1, 5 is good. And thanks to your help, we get the same answer. As you can see, it's easy to lose things in here, so be very careful when you're writing these out. Okay, but that's the main idea behind row echelon form. If you need me to review 2x2s, I can do that maybe tomorrow. Actually, we'll probably do it a little bit within eigenvectors and eigenvalues. So I'd like to start that. Okay, unless there's questions about row operations and how to transform matrices into the two forms. All right. Let's go on then to eigenvectors and eigenvalues. We're going to start by letting matrix A be a square matrix, so we'll say n by n. A number, which we'll call lambda, is said to be an eigenvalue of matrix A if there exists a non-zero solution vector which we'll call capital K, of the linear system, oops, mixing up my colors, A times K equals lambda times K. Okay, so this is the eigenvalue And this is what we mean by eigenvector. Yes?
Is A equal to lambda then?
Not quite. We'll go through it in a second. Here's an example. Verify that K, which we'll define here as 1, -1, 1, is an eigenvector of the matrix 0, -1, -3, 2, 3, 3, and -2, 1, 1. Okay, because remember, in this equation, what does A represent? A what? Matrix. Lambda is just a number. Okay? So what's happening here is if we take matrix A with matrix K, it's going to equal the same thing as some constant times that matrix, which we call the eigenvector. Okay, so to verify that K is an eigenvector for A, what we'll do is go ahead and compute A times K. Bless you. So if we multiply A with K, here we have a 3 by 3 times a 3 by 1, which will give me a product that is a 3 by 1 matrix. And what will that matrix look like if I do the multiplication? You guys remember how to multiply matrices by hand, right?
Yeah, you go down the first one, or across the first one.
You guys know what dot products mean now, right? You're essentially dotting each row with each column of the second matrix to figure out each entry. Does that make sense? So if you think of this as a vector with 3 entries, and this is a vector with 3 entries, you're just computing the dot product, right? So 0 times 1 is 0, -1 times 1 is 1, and then add that with -3, we get -2. Does that make sense? And then you take that idea, that notion, and you go through the rest of the rows and do the same thing. So now we take 2 and 1, 3 and -1, 3 and 1, take their products, find the sum of those. What do we get? And the last entry is? All right. So does this equal some constant times K, which was 1, -1, 1? What is it? -2. So this is the same thing as -2 times K. So we just verified that K is indeed an eigenvector of this matrix. Okay? Does that kind of explain a little bit better? So A is not equal to lambda because we have a matrix, we have a coefficient. Okay, it's just that the multiplication will reduce it to the same matrix on each side. Okay? So now your question hopefully is, okay, how do we actually find them? Because that's the big picture, is we want to be able to have a matrix at hand and find the eigenvalues and eigenvectors. Okay, so that's what we're going to talk about next. Actually, let's clarify this. So this is indeed an eigenvector corresponding to an eigenvalue of -2. Okay? All right. So, just using some matrix algebra properties. Let's go back to the definition. So, using the definition that A times the eigenvector is equal to some constant times the eigenvector. If I move this around and set it equal to 0, and then I pull out the K matrix, I'm going to throw in the identity matrix here because that's not going to change things. Okay, and now this is really the big part of where we get everything from. If we're trying to solve this equation here, there's one obvious solution, right? What would it be? K is equal to, yeah, but we don't want that one, right? So we're going to ignore that case. Because if it's 0, then really we don't have any eigenvalues, we don't have any eigenvectors, that just ruins the whole point. Okay, so what we're going to work with now is the fact that we want A minus lambda I to not be invertible. The only way to throw this case out is if I were to find the inverse of this matrix and apply it to both sides, right? That's how I would isolate K to get K equals 0. Since we don't want that case, then we are going to work with the fact that A minus lambda I does not have an inverse. If it doesn't have an inverse, then this throws away the fact that K could equal 0 possibly. Does that make sense? No? Yes? No? Okay. This number here, or this, what does this represent? Matrix or a number? Matrix. How do I get rid of matrices? What's that? That's involved in it, yep. Multiply by the inverse. If you multiply by the inverse of this, then the inverse of this matrix times this matrix would just give you an identity matrix, which is not going to do anything, right? And then you're left with just this matrix having to equal 0. Does that make sense? And that's the case that we don't want to include because we want the non-trivial stuff. Does that make sense? So if we don't want this to have an inverse, then we don't want it to be invertible. Does that make sense? And if we don't want it to be invertible, that means that A minus lambda I has to be singular, which means that the determinant, and I think, Rick, you were saying this, right? To find the inverse, you have to use the determinant. Okay? One of the conditions was that if there was an inverse, the determinant could never equal 0, right? Well, now we're working with the other case that we, in fact, do want the determinant of this matrix to equal 0, because that's the only way that it's not going to have an inverse. Okay? This is the key. This is going to lead, and I'm running out of time. That's okay. This leads to a polynomial. We'll talk about this on Monday. Who's going to be gone Monday? Raise your hands. 1, 2, 3, 4. Everyone else should. Okay. So I don't have just look on Edmodo for the last 15 minutes, okay, so that you guys aren't lost when you come back. It's not too bad. Anyway, if you solve this equation, if you actually find the determinant of this matrix, set it equal to 0, this leads to a polynomial in the variable lambda. The roots of the polynomial are the eigenvalues. Okay, so then what you would do is solve this. You augment a minus lambda I with 0, and you use each eigenvalue here. This is a good place to stop. So once you get this equation, to get your eigenvalues, you go back, you augment it with 0 to find out what the eigenvector is going to be. We'll talk about that procedure on Monday. Good place to stop. And all we have left are a couple problems. Okay, I'll see you guys.